Hello students, in lecture 11 of your course Elements of Discrete Mathematics, we are starting the graph theory, and in this very first lecture of graph theory, first we will consider the basic terminologies. So first you should know what is a graph. A graph G, mathematically or symbolically if we represent a graph G, is represented by this pair V comma E. So here this symbol V basically represents a non-empty set of vertices or nodes, and the symbol E represents the set of edges. Each edge has either one or two vertices associated with it, and these are called the endpoints. These are called the endpoints. So we can say that an edge is set to connect its endpoints. So you can see in this example. In this example, these dots are representing the vertices, and these lines are representing the edges between these vertices. For example, here we are having five edges: V1, edge V1, V2, V3, V4, and V5. These are the five vertices. And suppose we talk about these vertices V1 and V2, then we have an edge E3. This edge E3 is connecting these vertices V1 and V2. That is what we have said earlier. An edge is set to connect its endpoints, means it connects its endpoints. So V1 and V2 are the endpoints of the edge E3. Similarly, for this edge E2, V2 and V4 are the endpoints, and for this edge E7, V4 and V5 are the endpoints. Now look at the different situation. Here this edge E1, is starting from V2, and again it is ending at V2. That means for this particular edge, the end, we have only one end vertex, that is V2. So in such a situation, an edge is set to form a self loop if its end vertices are same. Now look at this another situation. Now between these two vertices V1 and V3, we can see this is one edge which is connecting these two vertices, that is E4, and another edge is E5, that is also connecting these two vertices. So now look at the statement. Two edges are said to be parallel if their end vertices are same. So definitely E4 is a different edge and E5 is a different edge, but their end vertices are same. So these two are called the parallel edges. So that is the concept of parallel edges in the graph. It is not like that the line should be parallel. In fact, here the concept of parallel edges means the edges which have the same endpoints. Those are called the parallel edges. Next is the definition of simple graph. A graph that neither has a self loop nor the parallel edges. Such a graph is called a simple graph. For example, in this graph you can see we have four vertices V1, V2, V3 and V4, and four edges E1, E2, E3 and E4. Now here you can see that there is no self loop, and neither a self loop and nor parallel edges. So that is why this type of graph is called a simple graph. So look at this remark. It should also be noted that in drawing a graph, it is immaterial whether the lines are drawn straight or curved, long or short. What is important? The important fact is that the incidence between the edges and the vertices. For example, you see the situation. Here we have the four vertices 1, 2, 3, and 4, and these are connected by edges. So I can say that the edge between the vertices 1 and 2, let I say this edge is E1, from 2 to 3 this is E2, and from 3 to 4 let this is E4, and from 1 to 4 or 4 to 1 whatever I say it is E5, one more edge is there, E6. So in fact you are having 6 edges and 4 vertices. Now look at the situation. Here the edges are drawn or edges has been represented with the help of straight lines. But we can also represent the edges with the help of curved lines. In fact, connectivity matters. Okay, in connectivity means you have to look for the vertices between which there is some edge exist. For example, here I put the vertices like that 1, 2, 3, and 4 in this way. I am putting it here. Now you see there is an edge between 1 and 2, and that edge we are calling E1. So there is an edge in this second representation, edge between 1 to 2, we are calling it as E1. Then from 2 to 3, we are calling it as E2. Then 3 to 4, we are calling it as E4. And 4 to 1 is E5. And between 2 and 4, this is E6. Now, this is the one graph, and it is having two types of the representation. In fact, you can see here between two edges, between two vertices, we have an edge E1. So E1 is there. So that way both the representations are same. These two graphs are same. These two graphs are same, not the different. Only the representation is different because in this graph the vertex set has the elements 1, 2, 3, 4, and the edge set consists the elements E1. These are the edges E1, E2, E3, E4, E5, and E6. So both the sets, both these graphs are having these elements only. The vertex set consists these elements and edge set consists these elements. So the representation is G equal to VE for both of these graphs, but have been represented differently. The next is a point you should note. In some graphs, two or more edges seem to intersect at a point, but the point of intersection does not represent a vertex. For example, look at this situation. Here we have having these vertices, suppose V1, V2, and here we are saying that this is V3 and this is V4. And these are the edges represented, that between V1 and V2 we have an edge A, between V2 and V3 we have B, V3 to V4 we have C, and V4 to V1 again we have the edge D. Now the point to be noted here is regarding these two edges. This edge joining V1 and V3 is represented by E, and the edge joining the vertices V2 and V4 is represented by F. Now look at the situation here. These two edges seems to be intersecting at this point. So in fact this point is not a new vertex. It is due to the representation it is looking like that, but in fact they are not intersecting. In fact this E is showing the connection between V1 and V3. So I can put in a different way. For example, here the another representation is V1. Here this is V2, then here V3, and this is V4. So I can stretch this E to this side. So now you can see, in fact, V1 and V3 are connected through the edge E, but now it is not intersecting this F. So this kind of intersection does not show you that it is a vertex. In fact, it is just a connection between these two vertices, which can be shown this way or that way. Next definition is degree of a vertex. the degree of a vertex in an undirected graph. So here the term has been used, the undirected graph. There are two types of the graphs. One is the directed and another is the undirected graph. The directed graph consists the direction, and in undirected graph there is no direction. And for example, this one is an undirected graph. We are not showing the direction that this edge is v1 to v2 or v2 to v1. So we can go both way, v1 to v2 or v2 to v1. But in case of the directed graphs, the edges have some direction. For example, if v1 is here and v2 is here, and this is the edge E1, then you will say that edge E1 is from V1 to V2. So in fact, E1 can be represented by V1, V2. So this is the situation for the directed graph. But here we are dealing with the undirected graphs because there is no representation regarding the direction of the edges. So I'm coming to the degree of a vertex. What is the degree of a vertex? The degree of a vertex in an undirected graph is the number of edges incident with it. Number of edges incident with it, except that a loop at a vertex contributes twice to the degree of that vertex. The degree of vertex V is denoted by deg of V, degree of V. Now, see this graph here. We have 6 vertices represented by this blue color, V1, V2, V3, V4, V5 and V6 here. And if I want to calculate the degree of V1, so V1 you can say how many edges are incident upon this V. This is one edge, the second edge, the third and the fourth, means 4 edges are incidenting upon this vertex V1. So degree of V1 is 4. Now look at V2. At V2, how many edges are incidenting? 1, 2 and 3. So that is why degree of V2 is 3. Similarly, degree of V3, V4, V5 you can calculate. You can see V5 only 2 vertices are incident upon, two edges are incident upon this vertex. So therefore degree of V5 is 2. Now if we see this V6, so on V6 only one edge is incidenting. So one edge is incident upon this vertex V6, therefore degree of V6 is 1. So now see this definition. A vertex of degree 0 is called a pendant vertex, and degree 1, here vertex of this is called degree 1 is called pendant vertex. But we can also have a vertex of degree 0. Suppose I add another vertex V7 here, then you can see this vertex has no edge incident upon it. So degree of V7 in this situation is 0. So for a vertex whose degree is 0, that is called an isolated vertex. A vertex whose degree is 0 is called an isolated vertex. For example, in this situation, V7 will be called an isolated vertex and V6 is called a pendant vertex because its degree is 1. Next is the statement, the handshaking theorem, or sometimes in some books it is written as handshaking lemma. So what is the statement here? Let G equal to VE be an undirected graph with m edges. With m edges, then sum of the degrees of all the vertices. In fact, the meaning of this right hand side is the sum of the degrees of all the vertices is equal to twice of m. Is equal to twice of m. So this is the lemma. In any graph you can verify this. So based on this lemma, In fact, you can say sum of the degrees will be equal to twice of m. So from here you can also conclude that in any graph the sum of the degrees of all the vertices is an even number. This is an even number. This is another way to state the same thing. Now we have one theorem. An undirected graph has even number of vertices of odd degree. Even number of vertices of odd degree. The meaning, you just understand the statement. Suppose we have a graph. Suppose we have a graph like this. You can say in this graph, certain vertices are there, v1, v2, v3, v4, and v5. So number of you can see the degree. I am writing the degree of each of the vertex here. Degree of this vertex is 3. Degree of this vertex is 1. Degree of this vertex is 1, 2, 3. This degree is 1 and this is 2. So now you tell me the vertices with even degree equal to, what are the vertices whose degree is even? Here is v5, its degree is even, that is 2. Means only one vertex is of even degree. Now the vertices with odd degree equal to how much? Number 1 is v1 is of odd degree, v2 is of odd degree, v3 is of odd degree, v4 is of odd degree. So what is the total number? Total number is 4, and 4 is an even number. So this is the meaning of statement. Whenever you have any undirected graph, then it has an even number of vertices of odd degree. So vertices of odd degree are 4. Therefore, number of vertices of odd degree is an even number. That is, 4 is an even number in this case. You draw any graph. In every graph, you will find this situation. The vertices of odd degree, the total number of vertices of odd degree will be an even number. This statement we should prove, we will prove here in general. Okay, so let us talk about a graph GVE. Now V is the set of all vertices, and among those vertices, some vertices will be of even degree and some vertices will be of odd degree. So let us break this V in two parts, that V1 union V2. V1 is the set of vertices which are of even degree. Here we are breaking in two parts, V1 and V2. Set of vertices of even degree and set of vertices of odd degree. Means V2 consists those vertices whose degree is even, and V2 consists those vertices whose degree are odd. In this way, from the handshaking lemma, we have 2m equal to sum of the degrees of the all vertices. V belongs to V. But now you have broken this V in two parts, V1 and V2. So that is why the summation is broken in two parts. This is the summation over the elements of V1 and this is the summation over elements of V2. Now, because degree V is even if V belongs to V1, because as we mentioned, this V1 consists those whose degree is even, V2 consists those whose degree is odd. So here all the values are even and sum of the even numbers is again even. So in fact this whole term is an even number. Also in the left hand side there is an even number. Now you know that if in left hand side this is even number and right hand side is sum of two terms, then an even number can be obtained either both if you add two odd numbers or if you add two even numbers. An even number cannot be obtained by the addition of one even number and other odd number. So it is not possible. So in fact, it has to be an even number. But now in the situation you see here, this V2 is the set of those vertices whose degrees are odd. That means each of this number which you obtain here is odd. So how many times you should add an odd number so that you obtain an even number in total. So definitely an odd number is should be added even number of times, only then we can obtain an even number. I want to explicitly explain this like this. Suppose you have three odd number and again odd number is 1, again you have odd number 5, 7. So if you add 3 plus 1 plus 5 plus 7, then you can have 4 plus 5, 9, 16. So this is an even number. And you have added it how many times? Even number of times. Now if you consider the numbers like 1, 7, 3, this is odd number of times. If you add, you will get 11. So this will not be an even number. So definitely in order to obtain an even number from the addition of odd numbers, then odd numbers should be added even number of times. So here you can say this V2 must consist, this set V2 must consist even number of edges, even number of even number of vertices. This V2 must consist even number of vertices. That is what we wanted to prove here. An undirected graph has even number of vertices of odd degree. Even number of vertices of odd degree. So that is what written over here. You can understand it. Next, when UV is an edge of a directed graph G. For example, we are talking about a directed graph and U is here and V is here. Then this edge E, as I told you, can be represented as UV by this pair. Definitely then it will be a directed graph. When UV is an edge of a directed graph G with directed edges, U is said to be adjacent to V and V is said to be adjacent to U. The vertex U is called the initial vertex because you are starting from here and going in this direction. And V is called the terminal or the end vertex of this edge UV. The initial vertex and terminal vertex of a loop remains same. Suppose we are having U, and if we have a loop like that, then initial and terminal vertex are same in case of a loop. Now we are defining some special graphs. Complete graph first. The definition is complete graph. A complete graph of n vertices is denoted by Kn. And the first thing is that a complete graph is a simple graph. Simple graph means it will have no loops and no parallel edges. That contains exactly one edge between pair of distinct vertices. The graph Kn for n equal to, in fact, we are representing from n equal to 3, 4, 5 and 6 that are displayed in the figure. A simple graph for which there is at least one pair of distinct vertices are not connected by an edge is called non-complete. So here all these are the examples of complete graph. So this is complete graph of 3 vertices, this is complete graph of 4 vertices, complete graph of 5 vertices, and complete graph of 6 vertices. In fact, you can see there exists an edge between every pair of the vertices. Between every pair of the vertices there exists an edge. Suppose if in place of this, if I write that this is the graph of 4 vertices, if I am writing this is not complete graph because there is no edge between these two vertices. There is no edge between these two vertices. So, but now if we are joining these, so you can say now you consider any pair of two vertices, there will exist an edge. So such a graph is called a complete graph. So this is complete graph of uh, four vertices. This is complete graph of 5 vertices, and this is complete graph of 6 vertices. And also note that in a complete graph, uh, no two vertices should be connected by more than one edge. Even if we write it like this is complete, but once you do this will not be a complete graph. Fine. Similarly, next is the definition of cycle. A cycle Cn n greater than equal to 3 consists of n vertices v1, v2, vn, and the edge is v1 to v2, v2 to v3, v3 to and vn to vn minus 1 to vn, and vn to 1. Means you will start, for example, for this case, this is v1, this is v2, and v3. So we have an edge v1 to v2, v2 to v3, then v3 to v1. Means we arrive at v1 again by traveling through all the vertices. For example, here we can talk about v1, v2, v3, v4. So v1 to v2, v2 to v3, v3 to v4, and v4 to v1. So in general, that has been written here v1 to v2, v2 to v3, and so on, vn minus 1 to vn, and then vn to finally we again arrive at v1. So such a situation, if we have such kind of graphs, then those are called the cyclic graphs. Here we have the cyclic graphs for the vertices 3, 4, 5, and 6. So this is the exercise for your practice. In these 1, 2, 3 exercises, find the number of vertices, the number of edges, and the degree of each vertex in the given undirected graphs, and identify the isolated and pendant vertices. So in each of these graphs, do all the things, find all the things here. Now, next question is, can a simple graph exist with 15 vertices, each of degree 5? So you should try to do this. And next question, what does the degree of vertex represent in an academic collaboration graph? Academic collaboration graph. And what does the neighborhood of a vertex represent? And what do isolated? In fact, I have not written the definition of neighborhood of a vertex. You try to find it out. And it is given in the book Kiescher. So what do isolated and pendant vertices represents? So these are the exercises for your practice, and that's it about this lecture. Thank you.